Howdy.
Hi, good morning. Wow, we got a big crew today. This is great.
Oh, I can't see him. I said I couldn't see him. I hate being in person when you can't see him.
Oh, you'll see me. I'll be standing up.
Okay.
I just have to sit here and log people in, so.
Did you see my email that I sent you?
I did, yeah.
I was just making sure that you saw it. That I sent them.
Yeah,
Can I use the restroom?
sure.
Thank you.
So is one of you Jalen? No? Okay. What are your names?
Isabel.
Isabel. Oh, that's right. I didn't
Yeah.
recognize you with the mask.
Yeah.
Okay.
Shelby.
Shelby, okay, yeah, all right. I haven't seen you two very often. I saw you a little bit in your labs, but with the mask, just hard to recognize people, at least from
For
the
sure.
Okay, we'll go ahead and get started. Can the people on Zoom hear me, and can you see the slide?
Yeah, we can hear you and see the slides,
Okay,
or we
thank
can see
you.
the quiz.
Yeah, thanks. Okay, so what we're going to do today is I'm going to review the quiz that you took on Tuesday. So go over the answers for that. So if you have any questions, let me know as we go through that. And then we're going to finish chapter 12 today. And then what that means is on Tuesday of next week, so next class, we'll have our first full exam, which will cover chapters 11 and 12. And so just as the quiz was, that'll be over Canvas. So you don't need to come into the class for that. You can just take that wherever, but it will be available during the class time only. And so that's in general, for those of you who are new to the class, how it's always done is the quiz or exam is available during that period of time. And you have a little bit of flexibility when you start and stop, and then it is timed again. So it'll be worth 100 points versus this quiz, which was worth 30. So it'll be longer in terms of number of questions and time that you have. Okay? Yeah.
So is it, do we get the full class time to do it, or is it less time than the class, like the hour, less than an hour 20?
Yeah, it'll be less than an hour and 20. I try and give you what I think is enough time that you can complete it, but yet you can't just look everything up. That's kind of the idea behind it. If this was normal, like non-COVID, where everyone was in person and we were all sitting here, and you wouldn't have access to other resources, then you'd have the whole time. But just this year, because of the COVID stuff and a bunch of people being on Zoom, some being in the, it's just different this year. So you can decide if that's a good different, bad different, but the end result is it is different. And that's why you kind of have the pain in the neck thing of when you got to show work on certain problems, you got to figure, part of it is figuring out how to type it in so I can understand what you're saying and all that rather than just writing it. And, one thing I would say about that is I understand that it's difficult to, type the stuff in when you got to show your work on those problems. So if it was me personally, I'd be working it out on a piece of paper and then just copying it over, but you just got to build that into your time a little bit. Okay. And the other reason for showing your work is, sometimes people get it all set up correctly and do a lot of the calculations correctly and make a math error on the last step or something like that. That way you'll get some points. Whereas if it wasn't show your work, then it would just be simply get points or don't. Now, if you just put some stuff in and it shows that you really weren't progressing on getting the problem finished, you're probably not going to get any points there. But there are instances, I always have instances where people do a lot of things and set it up right, but they like miscalculate or something. In that case, if I can see that and it looks pretty clear to me that you knew what you were doing, you won't get full credit, but you will get some. So, okay, let's go through this quiz. So the first one, in this question, you're talking about gases and liquids, and basically want to know, do they compress or condense or whatever, and then how do they fit into the container? So the correct answer is the gas is compressible, and it assumes the volume and shape of the container, and then a liquid is not compressible, and it takes the shape of a portion of the container. And so if you have a container and you put a gas in it, it will expand to however big that container is. Whether it's a small container or a big container, it fills up the whole thing. And gases, we know we can compress, and that's where that whole concept of pressure and things like that came into play. Liquids are slightly different. You can't compress them. But if you have, say, 100 mils of a solution and you put it in a 100 mil beaker, it'll fill that beaker up. but if you put it in a 1 liter beaker, it just fills 100 mils up. So it doesn't do that expansion or that. So that's the difference there. Then number 2, which molecule is hydrogen bonding as the predominant intermolecular force? So remember when we talk about hydrogen bonding, there's 2 things we need. One is we need hydrogen, of course. And several of these had hydrogen, but what they didn't have is hydrogen bonded to either an oxygen, a nitrogen, or a fluorine. So you need that additional thing. Because of that, that meant that CH3OH, which is methanol, that's the correct answer there. The next one, when KBr dissolves in water, aqueous, potassium plus, and bromine minus ions result. The force of attraction that exists between the potassium cation and water is called a, well, you have an ion here. You have an ion here, the potassium ion, and then you have water. Water is a polar molecule, so it means you have an ion dipole interaction. So that positively charged cations going to interact with the negative portion of the dipole in water. Number 4, the intermolecular forces. Scroll up here. Intermolecular forces responsible for the fact that methane, CH4, sorry about that. The intermolecular forces responsible for the fact that methane, CH4, has the lowest boiling point, and it gives you this set of alkanes. The answer is dispersion forces. So once again, they all have hydrogen in them, but they don't have that hydrogen bonded to an oxygen or nitrogen or fluorine. So there's no hydrogen bonding going on. These are all non-polar. There's nothing polar in them. So there's no dipole-dipole. So that leaves us with dispersion forces only. The next one, what type of intermolecular forces exist between CH3OH, which is methanol, and H2O, which is water? You always have dispersion forces, okay? That's just a given. In this case, we also have dipole-dipole, and we have hydrogen bonding. So we got 3 things going on here. Number 6, the shape of a liquid's meniscus is determined by, so it's determined by the relative magnitudes of the cohesive forces within the liquid. So in other words, the forces within the liquid that are going on, and then the adhesive forces between the liquid and the container. The example we had in class was where we showed water, and then we showed mercury, and we showed how the water meniscus kind of went up on the sides because of those interactions. And the mercury was kind of the opposite, went down on the sides on that. Number 7, the property responsible for the beating up. Let me scroll down here so you can see it. For the beating up of water, that's surface tension. And then number 8 is asking which of these processes are exothermic, and we had melting, subliming, freezing, boiling, and then another choice was all of the above. Exothermic means heat's getting given off, and so the answer is C, freezing. For melting, subliming, and boiling, we have to put energy in, so those processes would be endothermic. Number 9, of the following substances, which has the highest boiling point? So once again, if we're trying to figure out which has the highest boiling point is going to be the one that in solution, which one has the most intermolecular forces. And so if we look at our choices here, it kind of comes down to the diol, so the one with the 2 hydroxide groups, so HO, CH2, CH2, CH2OH, and then the alcohol CH3, CH2OH. I say that because of that OH in there, we know that there's hydrogen bonding, right? And hydrogen bonding of those intermolecular forces was a pretty strong one. But in the first choice, the diol is a term for molecules that have these two OH groups on them. The diol one, we have two opportunities for hydrogen bonding. The alcohol, the CH3CH2OH, we only have one. So we're expecting to have more hydrogen bonding on that, and so that is the highest boiling point. Okay, so that brings us to number 10. So, you know, I think people in general did pretty well on 1 through 9. 1 through 9 was more some of the conceptual stuff of what we talked about. And so that was good to see that people, I think, had a pretty good feel for that. Most people did fairly well on that. Number 10 is where I saw a little bit more issue with responses in that. And so I want to talk about the problem a little bit, because I guarantee you, you'll see a problem like this on the exam. You know, it won't be the same problem or anything like that, but it'll be a similar type of idea. And if you recall, one of the things we talked about was we had that one diagram which kind of showed the transitions in terms of temperature change and then what happens when you get there to have a phase change and all that. And that's real important, that you're able to look at these kind of problems and from a conceptual point of view, break it up like that. If you can do that successfully, you're usually going to get the problem right. Not all the time, but usually, because then it's a matter of just plugging in the numbers and making sure you do the math right and stuff like that. So I want to talk about this one a little bit in terms of that. So we're told that we have 25 grams of ice, and we want to calculate the total enthalpy change in kilojoules associated with taking that ice and taking it to water vapor at 109 degrees C. So there's two things you needed to recognize here, since it's water. One is, you should know, hopefully you do, that water freezes at 0 degrees C. The other thing is that water boils at 100 degrees C. So even though that wasn't given in the problem, I think that's the kind of knowledge that you should have and most people would know. If it's some other weirdo chemical, anything other than water, then you would be given the boiling, what the boiling point is, what the freezing point is. But water, I think there's kind of an expectation you would know that, but you needed to know that. So then if we look at what they're saying is, in the problem, we're saying that we're starting at -4 degrees. If we're at -4 degrees, that means the water's frozen, right? Because the freezing point is 0. So the first step is we need to calculate an energy involved with taking that water from -4 to 0 degrees. So that would be the first thing you would calculate. And we'll go through the calculations here in a moment, but I just want to talk about it from a phase change and what's going on perspective first. Once we get to that freezing point of 0, then we got to change all that over from solid to liquid. So that's the second thing we would calculate. Well, then the third step now is we need to then raise the temperature of that liquid from 0 degrees up to 100 degrees, because that's the boiling point. So there's our third calculation we'll do. Then once we're there at that 100 degrees, we got to convert it off from liquid to gas. There's another calculation for you. And then the final step is going from 100 degrees to 109 degrees. So we had each of those steps that we needed to do a calculation around. And we're given some information around specific heats for water, for ice, water, and steam. So in other words, solid, liquid, gas. Excuse me. We're given the delta H of fusion, the delta H of vaporization. So we're given the constants that we need to have in order to solve the problem. So the key is we got all the info we need. We just need to make sure that we're breaking it up into those steps to get to the final thing. So one of the things I did right off the bat is I calculated the molecular weight of water. Because I know from my constants at some point I'm going to have moles. And so molecular weight of water, 2 hydrogens, 1 oxygen, total of 18. Well, here in this first step, I said we're going to go from minus 4 degrees to 0. So there my delta T is 4. And so my constant is in units of joules, gram, Kelvin. So I have my temperature difference of 4. I have my grams of water multiply, so grams of water cancel, temperature cancels, and now I get a value in joules, 209 joules. Remember, we want the answer reported in kilojoules, so at some point we're going to have to switch it to kilojoules. I went ahead and did that. If you have joules, and when I go to kilojoules, the easiest thing to do is slide the decimal over 3 places, okay? So now that takes care of the energy needed to go from minus 4 to 0 degrees. Now we need to convert the water from solid to liquid. So here's where the constant for that is 6.01 kilojoules per mole. So I need to take my mass of water, 25 grams, convert it to moles. I do that using my molecular weight, which I calculated earlier. And then now my moles units cancel here, and I'm left with kilojoules there. So I've got my second one calculated. Now the next one is I need to go up to the boiling point. So I'm going from 0 degrees to 100. That delta T is 100. So using that second constant, the 4.18 joules grams Kelvin, so similar to what I did up previously. And then that comes out to 10,450 joules. I move that decimal over 3 places. It's 10.4 kilojoules. Okay, so now I'm sitting at 100 degrees. I'm going to do that conversion from liquid to gas. Use that constant of 40.67 kilojoules per mole. Convert the grams to moles again, and I get 56.5 kilojoules. And then the final step is to go ahead and do this last increase in temperature from 100 to 109. So my delta T there for that transition is 9 degrees using that 1.84 value constant, and I get 415 joules or 0.414. So I've gone through, I've calculated the energy, the heat flow for all of that. And so now I just simply add up all those numbers. And if I do that correctly, I get 75.9 kilojoules. So a bunch of steps to it, a lot of calculations to do it. A lot of opportunity to mess up, unfortunately. But the key though is thinking about the processes that are going on. To be honest, if you can keep that straight and get that clear, that's half the battle. Because after that, I'm kind of repeating the same calculations over. I'm just using different constants for the different phases and all that. And so if I can be clear on what's happening and kind of think about that from a conceptual point of view. And like I said, everybody did pretty well on the conceptual type questions in the first part of the quiz. So I would encourage you to apply that kind of thinking to problems like this. Okay, any questions on this problem or any of the other stuff on the quiz? Okay. All right, I'm going to pull up the slides for chapter 12 and then we'll go from there. So hold on a second. Okay, so we've been talking about solids. I think the last one we talked about was molecular solids, and now I'd like to talk about another one, this covalent network of solids. And so when we talk about covalent network, what we're talking about is each of these, in this case, carb atoms, represented by the balls in the diagram, are covalently bonded to each other. And we think about covalent bonds, and we said those are the strong bonds. Those are the strong ones. So now if we've got atoms that have multiple covalent bonds to them, that should be an indication to us that things are really going to get strong. And that's exactly what happens here. So in this case, we have these atoms that are covalently bonded over distances within the framework of this lattice and this pattern of atoms. And as we get that bonding going on, and it's stronger and stronger, the material is going to be harder from a physical perspective, and it's going to have higher melting points. Because remember, we said the stronger those interactions, the higher the melting point type of property it has. In this particular example where it's all carbon, this is what diamond looks like. So you have these tetrahedron shapes of the carbon atoms, and then that covalent bonding makes it really, really strong. And if you think about it, diamonds are a very strong material. You know, usually you think of them in terms of jewelry and they look nice, but they also have a lot of industrial applications because they're very strong and so they can do cutting and things like that. So another type of this covalent bonding material centers around the semiconductor industry. And so semiconductors, we're going to talk about those a little bit. And one of the things I just want to refresh your memory on is over here on the right is this molecular orbital diagram. So remember, we've talked about the molecular orbitals last semester and a little bit more this semester. And what we say here is on the left and on the right, we have the atomic orbitals, in this case, s orbitals and p orbitals. And then in the middle, we draw the molecular orbitals. And however many of those atomic orbitals we're using, that sum is how many molecular orbitals we're going to have. And if we drew out the molecular orbitals in detail, we have bonding molecular orbitals down here on the bottom, kind of in this blue box where it says valence band. And then we have the anti-bonding molecular orbitals up in this kind of pinkish box where it says conduction band. If you recall, we said a little earlier this semester that as we get into these types of materials, we're going to draw it more it's kind of smearing of things rather than the individual molecular orbitals like we did some last semester. And that's what we're doing here. We're calling the bottom is the valence band, molecular orbitals, and the conduction band up on top. And also this, just think of this corresponding to the bonding down here at valence and the antibonding up there in conduction. And remember, we always said that if valence, in other words, this bonding molecular orbitals are full and the antibody are not, that's a more stable, more likely configuration for a molecule. So I am going to introduce a new term here, is that the difference in energy between this valence band and this conduction band is something called the band gap. So there's energy associated with this. Remember, this y-axis is the energy axis. And so as we go up, that's more higher and higher energy. As this distance changes, gets smaller or bigger, this band gap energy changes as well. If the band gap is less than 3.5 electron volts, in other words, if this energy that we have labeled band gap is less than 3.5 electron volts, then the material will not be an insulator. If it's over that, it's just an insulator. And that doesn't really do us any good for what we're trying to do here. So in semiconductors, what you want is you want electrons to be able to move from this valence band into the conduction band. You want to be able to move across that. So what the band gap is telling us, if that difference is too big, energy is too big, that won't happen. And then it's not going to work as a semiconductor. The way it turns out is the group 4A elements have small enough band gaps in their molecular orbital diagrams that they can act as semiconductors. And if you recall, some of the group 4A elements, the ones we're particularly interested in, silicon, germanium, tin are three examples that are fairly common in the semiconductor world. Silicon in particular, you always hear about silicon wafers and silicon chips and all of that kind of stuff. This is why. its band gap property is such that it's less than that 3.5 electron volts. And so you get this movement of the electrons within it. We'll see a little bit later what that means exactly. But that's why that is. The other thing we're going to see is that anymore, you usually don't have just pure silicon or something like that. They do what they call doping, where they put some other elements in. And we'll talk about that a little bit as well, what that means and why that's important. So the key thing to the 4A elements, and remember, the 4A means that's the column it is in the periodic table. So if it's 4A, we remember that that means there's 4 valence electrons, right? And so what's been found is that having that 4 valence electrons there, that's a really good property for something to work as a semiconductor. Once again, it goes back to that band gap stuff. There are combinations. So here's gallium and arsenic, gallium arsenide. And while neither of those has 4 valence electrons, gallium has 3, arsenic has 5, so the average is 4. So then when you go to do that molecular orbital diagram, you'd have a total of 8 electrons, the same as if they were both 4 and 4. So it's been found that some of these combinations like this, because of winding up with that same number of valence electrons, you wind up with band gap energies that are small enough so that once again, they can be semiconductors. So some of the combinations and stuff like that get kind of complicated. We're not trying to go into that. But here are some examples of some things in the band gaps. And remember, so in this table, this E sub G electron volt column, that's the band gap. And we said for it to be an effective semiconductor, it needs to be less than 3.5. So we have diamond, we have a zinc blend, we have gallium arsenide, we have zinc selenide, we have tin, we have indium, we have some others here. And we see all those are pretty small, pretty much less than 3.5. And we see all of these elements on the periodic table are kind of near each other. So this one with silicon, germanium, tin, that's our 4A column. And so each of those has the 4 valence electrons. If we go to the left of them, so like aluminum and those would have 3, zinc would have 2. Over here, where phosphorus is, we have 5 and 6. So you can see how you can get some combinations between those, which would wind up with that 4 plus 4 for the molecular orbital diagram. Okay. So let's talk about doping for a second. So over here, we have a molecular orbital diagram. So we're not showing the atomic orbitals, we're just showing the molecular orbitals. Down at the bottom, we have that valence band, which we have in blue. And on top, we have the pink, which is the conductance band. And so one of the things that you can do is to change the properties and to get some electron flow is to do what they call doping. And so by adding in an element that either is electron deficient or has some extra electrons. And then that creates either an N-type semiconductor or a P-type. So what we see here is we're assuming that from the material we have, our band gap is sufficient energy. So it's not above that 3.5 value. And then down at the bottom, we go and we say, okay, we're starting with the valence band. It's fully filled, that molecular orbital is fully filled. But then if we swap out something, now we can go where we have more electrons and we start to get some filling the empty molecular orbitals up above in the conductance band. And so now we have some blue up there. Or we can put something in that's electron deficient, And then what that does, it results in us not totally filling the valence band. So semiconductors that have more electrons are called N-type semiconductors. So this second one, this B diagram, would be an N-type semiconductor. For me, the way I always remember the difference between N and P-type semiconductors is that N, I think, negative. If it's negative, it means it must have picked up electrons, okay? Because electrons are negatively charged, so overall, it's going to have more of a negative charge. So that's how I think of negative N-type, more electrons. P-type semiconductors have fewer electrons, and so they say that there's a hole there. And so in other words, you have a gap in there where the electrons aren't all filled in, that's the hole. And then you can have electrons travel to try and fill in that hole. I think of P-type as P positive. Positive means you've lost an electron, you've lost some negative charge. So that's how I personally keep N-type and P-type semiconductors kind of clear in my head. So we'll get to in a moment what that means. And here's an example of where this comes into play. So if you're like me, you have a pocket calculator. And that pocket calculator, I never have to change the battery. Okay, it's got that little strip on top where you have to have light shine on it. So you have some energy getting into it. But then somehow it magically never runs out of charge. As long as there's a light bulb on or something, it works. That is photovoltaic energy at work, which is based on the semiconductors, this P and N stuff that we just talked about. And so, you know, that's not the fanciest thing, but it's a good example of what's going on. So you have that energy that comes from the light or the sun or whatever, okay? And then what it causes is, it causes electron flow, okay? Because you've got these semiconductors in there. And on the cartoon on the left, we see arsenic in the middle of all this silicon, and arsenic has extra electron, right? So it fills everything in. On the right, we have a P-type. In this case, we have a boron atom in the midst of all this silicon. Well, boron has one less electron, so that's what this open circle here is. That's a missing electron there. When you put these things together, and then you apply that light, then you can get movement of those electrons across there. And when that happens, when you have an N-type of silicon sample butted up against a P-type, you get what's called a P-N junction. So this junction, then the light hits it. So here's our solar energy, the light bulb or the sunlight or whatever it's coming from. It hits this P-N layer, okay? We have a P layer here, N layer, they're next to each other. We get that flow of electrons because of that, because we have the P-type material, remember? Which one is P-type again?
Fewer electrons.
It's losing, it doesn't have enough electrons, right? And then we have the N-type, which has more electrons, so those electrons can move over. As it does that, as we have this movement, then we generate electricity, okay? And that's why on those little calculators you don't have to have a battery, you don't have to plug it in, you don't have to whatever, okay? It'd be great if everything was like that, wouldn't it? If your cell phone was like that, if it gets a little more complicated when you're trying to do something other than a little pocket calculator, which is why you don't have that. But that's what's going on in this. So it all links back to kind of what we're saying here with this P and N type of semiconductors. And it goes back to our old friends' molecular orbital diagrams, okay? And this energy, this bond gap energy that we keep talking about, it has to be relatively low. And so that's why there's not a ton of things that you can do this. That's why semiconductors are always made of certain materials because of that bond gap. Okay, any questions about this part before I move on? All right. There are a couple of homework questions associated with this kind of last section that we did. I do want to spend a little time looking at one of them. So let me, oops. Let me move this out of the way so you can see that. Okay. So let's look at 1259. Let me pull that problem up. So in 1259, we're told that manganese sulfide, MS2, is the mineral that we're looking at. And it says it has a rock salt structure. Well, rock salt is sodium chloride. Remember, sodium chloride was one of those one atom to one atom configurations that we've talked about, I guess, a few days ago. And so one of the things that you should know is that that configuration is a face-centered cubic lattice, okay? So that's the kind of thing you're just gonna have to know. Once you know that, then you can calculate how many atoms from each of those elements is in there. So the sulfur, we have 8 times 1/8. Remember that 1/8 is like the contribution from the corner. Remember all of that stuff? You have the, based on, so if you don't remember, you want to refresh your memory on that. So based on the geometry, if it's on the face, it's half is in that unit cell. If it's a corner, it's an 8, things like that. That's where these 8 times 1/8 comes in, and 6 times 1/2, and then 12 times 1/4, and 1 times 1. So if it's a 1, that tells us it must be in the middle. Okay, so it goes back to spending some time, getting comfortable with those geometries and what that means in terms of how atoms are shared in the unit cells. So that's an expectation, is that you guys will know that stuff. So we do that correctly, we see there's 4 sulfur atoms and 4 manganese atoms. So great. We want to calculate the density of this, okay? So if you think about it, to have density, you need to know how many atoms you have. You need to know how much stuff is in there, because density, what's a common unit for density? What's the general thing with density? Anybody remember that? It's mass per volume, right? And mass can be expressed a lot of ways, but probably the most common is grams. Volume is usually expressed as milliliters, right? Well, but remember, we also said milliliters is exactly the same as centimeters cubed. And now we're talking about space. We said it's a face-centered cubic lattice, so we're talking about the space that a cube takes up. To calculate the volume of the cube, each of the sides are the same length, right? So then it's just length times width times height. So it's one of those lengths, one of those distances cubed. So what that tells me is I need to find out how many atoms I have, because that's going to tell me how much stuff is there. I need to get that number of atoms expressed into a weight. And then I need to know, well, what's the total volume that I'm working with? And that's that volume, in this case, of a cube. So here we go, and we take 4 atoms. We divide that by 6.02 times 10 to the 23rd atoms per mole. What does that number represent? Does anyone remember? I'm sorry, what is it?
Avogadro's number.
Avogadro's number, right. Whenever we have grams and want to get to moles like that, or rather atoms and want to get to moles, we use Avogadro's number. Then once we get to moles, then we can use the atomic weight to change that to grams. So this 32 number is the atomic weight of sulfur. That tells me how many grams of sulfur in 1 mole of sulfur. So I went from atoms, used Avogadro's number to get that converted to moles, and then use the atomic weight to get it to grams. And I can calculate then how much those 4 atoms weigh. I do the same thing for manganese. The only difference is now I'm using about 55, which is the molecular weight or the atomic weight of manganese. And I did a weight for the manganese. So the only thing then to do is, I said I want a density, which is grams per centimeter cubed, weight per volume. Well, the weight is going to be the sum of the weight of the two atoms, and that's what I have on my numerator here at the bottom. And then that's divided by the volume of the cube. So I have here the length of the side of the cube. The big thing I had to do is, if we go back up on top, you can see it was given to me in angstroms. Angstroms, that's 10 to the minus 10th meters. I want to be in centimeters. So I can convert angstroms to meters and then meters to centimeters by using the conversions for those. And once again, that's something you don't need to know how to do. Okay, so I know angstrom is 10 to the minus 10 meters, 1 meter is 100 centimeters. And so now up on top here, I've already converted my angstrom number from 5.223 angstroms to 5.223 times 10 to the minus 8 centimeters. That's the length of one of the sides of my cube. So now I'm going to cube that to get the volume. So here down at the bottom, once again, I have in the numerator, I have the sum of the two weights of the atoms that I calculated, divided by that side of the cube, length of the side of the cube cubed. And if I do all that math correctly, I get 4.06 grams per centimeter cubed. Okay? So just to talk about what I needed to think about to solve this, I needed to understand what kind of lattice it was. And I knew from sodium chloride, we talked about that in class and seen it in the book and in slides, that that's a face-centered cubic. Once I know it's face-centered cubic, then I can do this, well, how much of each atom is in that one cubic cell? And then that allows me to say, well, how much total atoms for each of these are present? And then I can use Avogadro's number and the atomic weights to go ahead and calculate out how much those atoms weigh. That gives me my numerator, because density is mass per volume. So now I've got my numerator, I'm good to go there. Then it's a matter of getting the denominator, which I need to get into centimeters cubed. Once again, I was given an angstrom, so I had to do some units conversion with dimensional analysis. And then I needed to just remember that the volume of a cube is the side cubed. Okay, any questions on this one? Yeah.
The 6.02 times 10 is like third.
Yeah.
How did you get that?
That's Avogadro's number. So we know that Avogadro, so in 1 mole, we know that there's that many pieces, whether it's atoms or whatever. It could be molecules, it could be atoms, it could be whatever. But that's Avogadro's number, and that's what allows us to go and get things, in this case, the things is atoms, to get things into moles. Okay, so that could be, this could be 4 molecules here, or 4 whatever. That's where the Avogadro's number comes in to help us with that conversion, okay? Anything else? Anything from any of the Zoom people? Okay, so we're gonna move on then to polymers. So when people think of polymers, they think of plastics, right? And that's pretty accurate. Polymers are kind of more the chemistry term for plastics. Plastics to me is kind of more of a generic term. And so when we're talking about polymers, what we're talking about are compounds that usually have a pretty large molecular weight. Okay, it can be hundreds or thousands or tens of thousands, you know, so pretty big molecular weight. And polymers are made by taking smaller molecules and attaching them to each other and doing that over and over and over and over and over. That's the poly part. Okay, poly means many. So it's over and over and over. And there's a couple different types of polymers that we'll talk about. But in general, you're talking about having two relatively small molecules, reacting them so they stick together and just repeating that over and over and over. So with polymers, you see what we call repeating units. So you will see the same thing over, and we'll see how that's written in a moment here. When we talk about types of plastics, I want to just talk about this table a little bit, because this is something that hopefully you're familiar with. If not, I would spend some time getting familiar with this, because there's all this talk about recycling of plastics and things like that. And so if you have some type of a plastic water bottle or something like that, or almost any plastic container, it almost always has a little number on it. That's what we see on the left here. Here we have listed 1 through 7. That number tells you what type of polymer it is, okay? And sometimes they have the abbreviation. So we see, like for 1, it can be PET or PETE, HDPE for 2, and on down the line. Sometimes they put that on. This picture down at the bottom, where you see the triangle, and then the number 1 in there, they always have that on. That triangle means recycling. That's why the arrows are going round and round. And the number tells me that this is number 1 here, polyethylene terephthalate. Okay. And here on this example, we actually have PETE written on there as well. Like I said, you don't always have that, but you always have the number. The reason why the number is important is most communities will not accept any plastic. There's certain plastics they'll accept. And so you want to check whatever it is you're thinking about recycling to see if it's one of the numbers that they accept. They almost all accept 1, 2, and 4. They usually accept 3. You get to 5, 6, 7, those they don't always accept. But it does vary from community to community. And you don't want to put the stuff in that they don't accept, because it just makes it more expensive and more difficult to do the recycling properly. So if you're not aware of these numbers on the plastics, it's probably worth just checking whatever you have to see what it is. That way, when you're at school and you're going by the recycling trash bin, you know which one to put it in. And I guarantee you, like for the water bottles, which a lot of people have, or the juice bottles, or all those are almost always recyclable, but it's worth checking just to be certain. So what you get is you get the number, there's abbreviations associated, and then over here on the far right-hand side, you have what actually the polymers are, okay? And we'll have some examples of what structurally, what that means. When we think of plastics, there's something called thermoplastics. Thermoplastics simply means that you can melt it and reshape it. Okay, so thermoplastic means heat's involved in making the manufacturing of whatever it is. Thermosetting plastics, you get a shape, and once you get that shape, you're kind of stuck with it because the reactions are reversible. And then elastomers are the ones that tend to be a little more stretchy and have that kind of elastic kind of comes out of that terminology. You think of something that's elastic, it's stretchy in that. When you make polymers, there's 2 kind of main ways that it's done. One is something called addition polymers. And that's where you have two molecules and you form a new molecule by they bond together, okay? And there's different ways you can do that, but fundamentally you take 2, you stick them together. Nothing in terms of atoms in that or molecules are gained or lost, they just get stuck together. Those are addition polymers. There's another way to do the reaction called condensation polymers. And if you think of condensation, you think of water, right? So in condensation polymers. Once again, you take a couple of small molecules, they get reacted so they stick together, but as a result of that reaction, you get a loss of water. We'll see an example of that in a moment. But first, let's look at an example of addition polymerization. So here we have a series of ethylene molecules. So ethylene is C2, C2, so we have double bonded carbons to each other. And what you have happen in this ethylene reaction to form polyethylene, you break this double bond, so you see that these arrows represent electrons moving out, and then that results in the carbons bonding to each other on down the line as single bonds. And so what you see is, so you start with 2 carbons, and then the hydrogens, so you have 2 carbons here, then 2 more carbons, 2 carbons. It just keeps going, okay, depending on how long you're in the reaction. So you open up that double bond, form new single bonds. That's an addition. We haven't added anything. We haven't added any atoms or anything like that. We're just taking what we have and just sticking it together, and on down the line it goes. For condensation polymerization, so the example we have here, on the left-hand side, you see nitrogen with 2 hydrogens. The other bond, they're not telling us what that is, that's okay. So this is called an amine group. We have nitrogen like that, that's an amine group. Then the next molecule that's reacting with, we have a carbon double bonded to an oxygen, and a single bond to an oxygen, and that oxygen bonded to a hydrogen. This whole functional group here, that carbon with the double bonded O and the OH, that's called a carboxyl group, carboxylic acid group. And so this carboxyl group, the OH from it will react with one of the hydrogens from the nitrogen. We see now we have 2 hydrogen and oxygen, that's water. And now we've got the carbon bonded to the nitrogen. So that loss of water, that water is kicked out when we do this reaction. That's the condensation reaction, okay? The other one, remember, we reacted this stuff together and we had some bond breaking and all that, but we didn't kick out any molecules or anything like that. Condensation, you kick out the water. So, but in each case, you're taking 2 small molecules, you're combining them together to make a larger molecule. And then in polymer chemistry, you do that over and over and over, and these things would repeat over and over. In a situation like this, where you have 2 different molecules reacting, this is called, so those individual molecules are called monomers. And so to form the polymer, that's called a copolymer. So a copolymer is when you take 2 different monomers and react them together. Versus this addition reaction that we looked at with ethylene, this would not be a copolymer because it's the same thing reacting with itself. Okay, so we were talking before about some names of some of these, and so I want to just look at this table for a second for a couple reasons. One is it allows you to attach some structural information with the name, and then I think, which is even more interesting on the right, is it tells you what some of the stuff is used for, these types of polymers, and why you have so many different ones. Before we do that, I just want to explain what this represents. So if you look at, let's look at the bottom one here, the polyvinyl chloride, PVC, and you'll see some things. You'll see CH2, CH2, and then there's a chlorine off this, or there's CH2, CH, and a chlorine off the CH. You'll also see brackets around it, okay? And then you'll see a bond going through each of those brackets. And you see a little N subscript down in the lower right-hand corner. What the N represents, if you were writing this out for a structure for polymer, you have some number there. And what that number tells you is it tells you how many of these repeating units you have. So if I had a 5 there, would mean I'd have 5 of these groups bonded to each other. So I'd have this CH2CH, then a CH2CH with the chlorine off of it, and CH2CH with the chlorine on down the line. Where the bracket cuts across with these bonds that are kind of sticking out, that just tells you those are the attachment points for the next groups, okay? And so that's the general way that polymer stuff is written. So the one thing you find in polymer chemistry is that a lot of times when these are made, you don't get all one for the end value. You get a range of things, you get a distribution, they call it. And so this allows you, the other thing this allows you to do is it allows you to write stuff out without having to sit. So say this was 20 units, it'd get kind of old writing that out 20 times. It'd be pretty long, hard to fit in your paper. So this is why the shorthand with the end came up. So I do want to point that out. That's just how the polymer world works. Why do we need so many polymers? Well, look at what we have on uses here. Let's look at polyethylene. Films, packaging, bottles. None of that's going to be too strong, in my opinion. If you think about a film, and by film we mean like saran wrap type stuff. Well, you don't want that so strong that you can't cut it or you can't tear it with your hands or something like that. That'd be a nightmare. Whereas you go down to PVC, polyvinyl chloride, well, you probably have heard of PVC pipes before. That's pretty common in plumbing for waste pipes and things like that. So you want that to be stronger, right? You want it to be resistant to the stuff that's flowing through it, so chemically resistant. You want it to have some strength, so like today when it's super cold, it doesn't freeze and crack. Or in the summer when it's really hot, it doesn't melt or something. Or if someone actually hits it, kicks it or something, it doesn't just shatter. So you would want a different physical property for plumbing type of pipe than you would for the saran wrap you're going to cover your sandwich with after you wrap it up or something. So all of these, and we have another table here as well, some other ones. One on top I like to point out is polyurethane. That's the foam stuffing in a lot of furniture. Okay, that's the foam stuff. And so you see different structures, but the key to that is it's for different uses. And based on what these polymer structures are and what the monomers were in terms of making the polymer, that's what gives it the physical strength. It gives us whatever other properties that you're looking for. Okay? When we talk about bulk properties of polymers, there's a couple things we need to remember, and that's what this drawing is helping us with. If you think of it as kind of this long rope type thing, because it's going to be a lot, these are big structures, right? They're not usually rigid, okay? And so what that means is they can kind of have different configurations, kind of flap around, kind of like in this picture you see. It almost kind of reminds you of a rope or something like that. As I said, a lot of times when the polymers are made, they don't make the exact same molecular weight. And so that's called chain length. And so you can have different chain lengths. And so you can imagine if one's longer than the other, might have some different properties there. So you got all this stuff that kind of goes in. Through all that kind of chaos, you do have some times where they line up, like we see in these circles here, where they sit on top of each other real well. And so that's where we start to get some order to it. And what did we say in this chapter about crystals and order and all that? Order is strength in the molecule world. And so in this example here, these areas where we have order and things are kind of laying on top of each other a little bit better, if they're laying on top of each other a little bit better, those dispersion forces are you're gonna get more intermolecular forces to keep it from, have it associated together. If it's associated together, it's a little more strength. So we're going to take a look at what that means in terms of how you can manipulate that if you want something that's a little bit stronger. And that short range stuff, those order regions, we call that crystallinity, okay? And once again, that fits in with the crystal stuff we've been talking about, right? Because we talked about when those crystals are really, the materials that form good crystals have pretty strong interactions, usually pretty strong material in that. So if you're trying to get a polymer that's stronger, okay, and you can define stronger different ways. You can say, is it denser, harder, less soluble, more resistant to heat, on and on and on. But if you're trying to do those things, then you want to try and get some more order here, more crystallinity. You can help that a little bit with some physical things, like mechanical stretching and pulling, things like that. But there's other ways to do it as well. We'll get to that in a second. But first, let's just take a look at this table and see some of this is all polyethylene, but the polyethylene is modified to get different amounts of crystallinity from 55 to 85%. And what we see is the melting point goes up a fair amount from 55 to 85%. So it's the same material, right? It's polyethylene, it's just those CH on down the line. So we haven't changed the composition. All we've done is introduced some more order somehow. And we see as we introduce more order, we get more interaction, and then now we get stronger material in terms of melting point. Density stays about the same. That makes sense because it's the same stuff. Stiffness, it gets stiffer as we introduce more structure. And yield stress, it gets higher too. The way to think of yield stress is if you're trying to break it or deform it or something like that, how much energy do you have to put in? Those tests are typically like a PSI type thing, pounds per square inch, but it's the amount of energy you got to put in to cause it to break or deform or something like that. So once again, it makes sense. We see these traits get more stiffness, more yield stress, higher melting point as we increase the order. And that's similar to kind of what we said about the other molecules. There is another way that you can change the physical properties, and that is by doing what they call cross-linking. And cross-linking means you take functional groups within the polymers and you react them across each other. So that's the cross-linking. So just, you got two things, you're linking it across, cross-linking. There's a process called vulcanization. Vulcanization is something that's done to make the rubber stronger. You don't hear that term very much anymore, but there was a time when people with tires that these had been vulcanized. It was supposed to make the tires stronger and last longer. And that's because in these types of polymers, there's these sulfur atoms, and you can cross-link the sulfur atoms. And so then now, this top polymer and the bottom polymer are actually linked together, and once again, more order, more crystallinity, so it's going to have more strength. So that cross-linking is a big deal. You do cross-linking polymer stuff all the time. That's a pretty common thing. So, okay, so now I want to just briefly talk about a couple things. Where the point isn't to make you experts in these next couple things, it's just so that you're aware of them a little bit. So if you hear the terms, you know what we're talking about. The first is nanomaterials. You hear this a fair amount where people talk about nanomaterials, big hot topic these days. A nanomaterial is something that is, dimensions are 1 to 100 nanometers in size. And remember, nanometer is 10 to the minus 9 meters. So we're talking about little stuff. Okay, that's the term nano. They've been trying to make semiconductors. Remember what we talked about a little earlier today, semiconductors. They've been trying to make them smaller and smaller. And one of the things you hear a fair amount these days are quantum dots. And quantum dots are just semiconductors made on a nanoscale. And so small molecules have discrete orbitals, macro scale materials have bands. Where does it switch over? And in theory, is 1 to 10 nanometers, about 10 to 100 atoms. So we're really talking tiny, tiny, tiny stuff going on here. And quantum dots take advantage of this. So they're this size. They're in this 1 to 10 nanometer, 10 to 100 atom size. And this gets back to band gaps and things like that. But you can think about it, if you can make semiconductors smaller and smaller, then it just means all your electronics can be smaller and smaller. If it's smaller, it takes up less space, it weighs less, all that. You can kind of, no pun intended, but you can connect the quantum dots on that one and figure out why that's a good thing. And the other thing that has happened, which has led to some study, was, I'm glad one person appreciated that joke.
I laughed.
Oh, okay. I was pretty impressed with myself on that, but anyway. Apparently no one on Zoom liked it. That's okay. You're probably muted. You're probably laughing really hard. Another thing that happened, and this was back in the 80s. I'm of the age, I remember when this came about and this was a big deal. There's something called buckyballs, okay? And so a buckyball is this C60 cage structure of carbon. So remember we talked about carbon could have that covalently bonded and you get the diamonds and it's really strong. And then, but that was like a tetrahedral shape. Graphite is the other form of carbon that we've known about, and that's in your pencil, so that's not very strong at all. You can break that pretty easily. But they discovered this buckyball thing, which kind of was shaped like a soccer ball, and it has 60 carbons in it, and you have that shape. But when it was discovered, it was a big deal, but no one knew what to do with it, okay? That was in the 80s. Well, as time went on, people started figuring out what they could do with it. And one of the things was getting it out of that ball shape, okay? So they figured out ways to it not always be in that ball shape. It's still bonded that way, but they could kind of flatten it out and do some things like that. And that's led to a bunch of new materials, the main one being carbon nanotubes, okay? And you may have heard of nanotubes, but one reason why those are of interest to people is, remember we talked about the doping of the semiconductors? That's not easy to do, okay? A lot of time and money goes to figure out how to do the doping. With these materials, they're finding that you can get the semiconductor properties without doing doping. And so if they could do that, and it has that strength still, then if you can start using some of this carbon-based stuff, in this case, they're showing us graphene down here, but this all came out of the buckyball stuff. If you can start making semiconductors without doing doping and et cetera, there's a bunch of value in that. So that's why you'll hear people talk about nanotubes, and you'll hear that in the news periodically. Once again, I'm not claiming to be an expert on this and don't expect you to be, but I think it's just good to hear about it a little bit. So there is a little bit of homework associated with this last part. And to be honest, the nanotubes, the buckyballs, the quantum dots, the nanomaterials, I think that stuff's interesting. I wouldn't spend a lot of time worrying about that on the test, okay? Polymers, yes. Some of the other stuff we talked about, yes. That's it for today's lecture. Does anyone have any questions about anything? Okay, does anyone want to still laugh about that connect the quantum dots joke? Feel free. So just to remind everyone, Tuesday will be an exam on chapters 11 and 12. So go into Canvas during class time and take the exam. And then I'll see you guys in person again on Thursday. All right, thank you.
Did you collect any more dirt?
No, I did not.
No, I didn't either.
I didn't have a